This is a series circuit, and it's a lot like what we did a couple of cards earlier, but that was measuring resistance, trying to teach you the relationships between the different types of resistors and resistances, I guess. This is actually, why reinvent the wheel? This is what I've been doing in class for nearly 20 years, and it works because the ratios are good. 100 to 50 is 2 to 1, 50 to 10 is 5 to 1, and 100 to 10 is 10 to 1. And if you do the Ohm's law math, which I'm going to show you here, then what you see is that the resistances with a given amount of current will produce a certain amount of heat, and that heat goes away forever, and that heat is the energy being converted from voltage into heat in this case. And we calculate the total resistance in a series circuit by just adding these up. So notice over here I gave you the answer. It's 160 ohms plus or minus a little bit. I can confirm that and get an actual number here. I'm going to try to be a little bit more precise here than I have been in some cases. According to this, I have 158.9. Okay, so I got my brand new super sharp pencil, 158.9. So it's really, move this for a second, 158.9 ohms. Can go to volts. Now voltage, remember, drops as you have a current flow. All right, I wasn't pushing hard enough. 12.36, 12.37. Now that'll drop a little bit. Make sure I got audio here. Yeah. And the voltage is about 12.36 volts. Remember, the beauty of these cards is you can write on them. Okay, so you don't have to worry about, you got some room over here. I suppose I could be using that, I guess. So if we did volts over ohms equals amps, 12.36 volts divided by 158.9 ohms, 12.36 volts over ohms. Say that over and over and over again. 158.9 equals 0.07778. So that equals, yeah, I can see I'm kind of light in the way here. 0.0778 amps, which works out to be about 77.8 milliamps. Okay, now, however, when we turn the circuit on, the terminal voltage here, I can actually put it where you can see it. The terminal voltage is going to drop, okay? So I would expect the current to be less than this because of two things. A, I expect the voltage to drop because we're applying a load, so we're going to lose voltage. And B, as the resistors heat up, their resistance will go up. So the voltage will go down and the resistance will go up. And volts over ohms equals amps. So if this number goes down, this number goes down. If this number goes up, this number goes down. I'm going to do this again. I had a little bit of a glitch. My fault. Dumbass move. That happens. Don't worry about it. Just move on. Anyway, let's do this again. And let's see if we get... This is rolling 0.7, as you saw, 0.8, 0.08, I'm sorry. Okay, so there's the rounded up, 0.08, because we're on a higher scale with a lower resolution. Now, if I move it down to millivolts, and I put it on damn, what a bad day. Milliamps, I'm expecting something slightly less than 77. I'll be reading in direct milliamps now. And sure enough, we get 74.5 74, which is close. It's not exact, but it's close. And what we're doing is we are turning the circuit on with the amp meter. And what I'm going to do is show you the voltage drops as we go through here so that you can see what's going on, and then I'll make some changes and so forth and so on. The key to understanding what we're doing here is to understanding that volts and ohms make amps, okay? The danger of learning this from a math perspective only, the danger is that people will say, oh, well, volts and amps make ohms, and that's not true. Or you know, ohms and amps make volts, and that's not true. What's true is that volts and ohms make amps, and that relationship is best expressed with this formula here, which is volts over ohms equals amps. And I don't really care about mathematicians saying you're supposed to simplify the equation, because that's dumb, because we're gonna de-simplify it anyway when we have to do it, when we start moving things around. So you might as well just start with this. So in case let me do this. Let's see if I can get this to work. Going milliamps. I've got my leads already plugged in here so I can have this thing going all the time. And that is 74.4 milliamps. Let me find something to put under here. There you go, 74.4 milliamps. Got another meter here for volts. And if we do the math, we take the 74.3 in this case, and that's again because the battery's losing some of its oomph. Okay. And we do this, all right? So we can do a couple of things. Okay, we can go a couple of different ways. Volts over ohms equals amps. And I've already calculated the total, but I don't know the voltage drop. So my voltage drop is equal to my amps times my ohms. Okay, so let's see if we get this. Oops, let me put this here, I guess. Yeah, there we go. That's easier to see. How about that? So voltage drop is equal to amps times ohms, because it's the amount of current flowing through the amount of restriction that determines how much heat is being used. So amperage is the flow flowing through the wire, and the resistance is what's holding it back, and that's the friction that produces heat, and voltage drop is technically heat. Okay, I have no idea where I am because the phone rang, and it was my son, and he was lost, and, well, that happens a lot. So, okay, so what I think I'm going to do here is I'm going to keep the 74.2 milliamps. I was trying to calculate the voltage drop of the 100 ohm, and since the voltage drop arrangement for Ohm's law is the voltage drop is equal to amps times ohms, we're going to take amps, which is 0.0742, because that's 74.2 milliamps. That's milli, so put a 0 in front of it to make it thousandths. 0.0474. Multiply that times the 100 ohm. But I don't know if it's exactly 100 ohm. Let me be more precise here. Might as well be more precise, right? Yep, 90. Whoops, close though. 99.8, 99.7. All right, we'll multiply that times 99.7. So we should get a 7.394, 7.397 volt drop. So we go back to volts, and this is one of the reasons I don't like volts and ohms, is because you got to go back and forth and back and forth and back and forth. All right, so let me read. No negative numbers. Okay, so we got a 7.4 calculated and a 7.44 measured, and that's probably because we turned off the switch and the resistors cooled down. But it's pretty doggone close. So 7.397 or 7.4 volts here, and the 7.4 volts here is here. Okay, now the ratio of the 100 to the 50 is 2 to 1. So that means this one should be half of this one, simply by virtue of the math. So if we take and figure out what the actual resistance is for the 50 and use it instead of using 49.2, all right, and we'll turn this back on, and we're at 74.3, so we'll do 0.0743 amps times 99.3, I think it was. What? That's not right. 40, oh. Dumbass. See, don't be afraid to make mistakes, all right? But know when something's wrong, because it's not right. As it was 49 point, I did 99. That's wrong. It's 49.2. Duh. Okay, so let me clear this out. 0.0743 amps times 49.2, which is half of that, so the number's going to be half, equals 3.655 or 3.656. So we'll turn this on. We get our amperage. Now we're going to read our voltage drop across the 50 ohm. Do this so you can see everything. And we get 3.662, and the calculation is 3.655. So again, something's a little higher. Either the resistance is a little lower because it's cool, or the voltage is a little higher than I anticipated. Okay, so we'll do the same thing for the 10. Well, it's 10 to 1 here. Well, this was 7.4, so I expect this to be pretty close to 0.74. And so we'll clear that out. We'll put 0.0743 amps times 10 ohms equals 0.743 volts. So let's do this. And we get 0.746. And the calculation was 0.743. So I'm a happy guy. And if we multiply this number times 5, because this is 5 times more, then we should get roughly 3.715, and I've got a mess going here, don't I? 3.657, so we're close, all right? So the ratios are important. It's important to understand that this amount of voltage and this amount of resistance is going to create a certain amount of amperage, and there it is. Now that I have all of my voltage drops, to prove a point, 7.44 plus 3.66 plus 0.75 equals 11.85. Let's see where our voltage is on the board. I'm not sure I've added those right. Nope, I'm missing something. Let me do this more precisely. I was being sloppy. I shouldn't be sloppy, should I? 7.44 plus 3.66 plus 0.746 equals, what are we doing here? We're losing something. I wonder, I hope it's not in the meter. No, not anything in the switch. Not really anything there. I got 4 millivolts. I got 4 millivolts in the fuse. Huh. Not much. The total is 11.84. So the math works out. So let me see if we can find the other. It's got to be here. There it is. Got a glitch in the meter. Interesting. I don't want to do that. There's 0.4. 0.404. Let's add 0.404 to this. 12.25. 12.25. I'm going to take it. I don't know what's going on in the meter. I think I may have a problem with the leads. In fact, I'm pretty sure that's what it is. There's a drop in the leads. And the resistance in the fuse. But we calculated 12.25 and we got 12.25. So I'm going to take it and I'm going to figure out what the heck's going on here. It didn't do what it was supposed to do, but it proves a point. Because if there's a drop in here, that has to add to these to get that. Okay. So at any rate, here's what I want to do real quick. I'm going to use a penny and show you if I drop the resistance by taking a resistor out, my amperage goes up. Okay. So by taking the 100 out, I've only got 60 ohms. And 12 over 6 is 2, so there's almost 200 milliamps. There's 110. And every time we change the resistance by making the resistance lower, it all works out. Okay? Now, I'm going to show you.